Okay, so the next one is exercise 4, and in fact the parts these parts we have already seen previously, so we have them solved elsewhere. So as a solution we will simply mention those things, that is where we encountered these things for the first time. See exercise 4a and exercise 18 of section 5, the fifth section. You may wonder why this repetition. Maybe the author thinks that the tools we have accumulated in this section somehow can be used to solve this in a new way. But I don't see the point, because the solutions we have of these things, they are pretty straightforward and easy, and the claims themselves are quite easy, both the parts. So we did not struggle with the solution so that we have to find a new solution which is easier than the already existing solution using more advanced tools. That is not the case here. I don't see that. Okay, anyway, if you find a solution which somehow uses tools of this current section in a very new way, then please let me know. We have the solution, that's the point. Next exercise 5. Using lemma 291, prove that a group of order p squared where p is a prime number must have a normal subgroup of order p. Okay, the solution. So we start off by assuming one such group. Let G be a group of order p squared. If we can find a subgroup H of G of order P, then by this lemma H would contain a non-trivial normal subgroup of G. Exactly how are we using this lemma here? And for that, let us also quickly recall the statement of this lemma. In this lemma, we have a finite group G and say there is a subgroup H of G such that this condition is true. The order of the group does not divide the index of the subgroup in the group factorial. Factorial of the index is not divisible by the order of the group. Then there exists a non-trivial normal subgroup of G. Let us call that N. Non-trivial means it's not equal to the trivial group having only one element, such that N is contained in H. This is what we have used here, where H is the subgroup. If we are able to find such a subgroup H, what type of subgroup whose order is P, then we are saying by this lemma H would contain a non-trivial normal subgroup of G. So the thing we have to see here is that this condition is being satisfied for such an H. How? You see, if H has order P, then because G has order P square, so the index of H would also be P, and P square does not divide P factorial. To see why this non-divisibility is true, we can show that also, since we are justifying everything. Let us see that also. If you consider this quotient, P factorial divided by P square, then you get, use the definition of P factorial, 2 times 1 P square. So if you cancel one P, you are left with this. Now P cannot divide this product because it is a prime. Why? That is because we know that if a prime number divides a product of some integers, then it has to divide at least one of them, which in this case is not possible because all the factors here in the numerator are less than P. So none of them is divisible by P, and that is why P square does not divide P factorial, and that is why we are able to use this lemma to conclude that G has a non-trivial normal subgroup that is contained in H. And now this has a consequence. This part we have seen, so I can wrap this up. But then by Lagrange's theorem, H is itself normal. Okay, then how is H normal? Because the normal subgroup of G, the non-trivial normal subgroup of G, let us call that N, that is contained in H, and H has order P. So being a subgroup of G that is contained in H, N is also a subgroup of H. So by Lagrange's theorem, the order of N should divide this order of P. Order of H, which is P. So order of N is either 1 or P. This is not possible because N is non-trivial. So order of N must be equal to P. But then both these groups have the same order and one of them is a subgroup of the other, so they must be equal, and that gives us the fact that H itself is normal in G. So that means if we can find a subgroup H of order P, then that implies that such a subgroup is normal. Normality is a consequence of having order P. Okay, so it's enough to find a subgroup of order P, and that's what we will now do. And in that search for a subgroup of order P, we will now consider the center of the group. Consider the center Z of G. Since G has order P square and we know that the center is a subgroup in any group, Lagrange's theorem gives us the possibilities that the order of the center is 1 or P or P square. Okay. If the order of the center is P square, then the center equals the whole group, and so G is abelian. Now G is a finite abelian group. In this case, we are under this situation. So in this situation, G is a finite abelian group whose order is divisible by P, F prime. Hence, by Cauchy's theorem for abelian groups, there is an element A different from the identity in G such that such that the pth power of A equals the identity. In this case, the cyclic subgroup generated by A has order P. Okay, how is it having order P? That is coming from this and this equation. This equation alone tells us that the order of A divides P, which itself is coming from I think exercise 36 in some which appears after some section. We have already come across that exercise, so we are using that and concluding that the order of A divides P. So it is either 1 or P, but then you use this one and that tells us that the order of A cannot be 1, because the identity element in any group is the only element of order 1. Other elements have orders greater than 1, all of them. So the order of A must be equal to P, and because of that the cyclic subgroup that A will generate will also have order P. So we wanted a subgroup of order P, we have got a subgroup of order P, if this is the situation, if order of Z is P square. Okay, now we consider this one. Oh, and we can in fact just simply mention this. If order of Z itself is P, then we don't have to do anything else, then we are done. Okay, so the only case now left is this. Now assume that the order of Z is 1. So the center is the trivial group. I mean, the center now is this group. But G itself has more than the identity element in it, because its order is P square, which for any prime P is greater than 1. P square is always greater than 1. And that is why now G is non-abelian, since order of G is P square, which is greater than 1, G is non-abelian. Choose an element B not equal to E in G. Again, such an element will be there in G because it has more than one element. And simultaneously and consider the cyclic subgroup generated by B, since B itself belongs to this cyclic subgroup, we cannot have, or let us write it as a positive statement, we have B not equal to the trivial group. Okay. Also, B is different from G itself, since G is non-abelian. And that is because the cyclic subgroup itself is, because it's cyclic, it is abelian, so it cannot possibly be equal to the whole group, which now is non-abelian. Hence, by Lagrange's theorem, the only possibility is this, that the order of this cyclic subgroup generated by P is P, because this is also like the other subgroups we considered. This is a subgroup of G, so its order is either 1 or P square. It cannot be 1 because of this, it cannot be P square because of this, so the only possibility that's left for us is this. So in any case, no matter what, we have shown that there is a subgroup of order P, and which by the argument in the beginning of the solution is automatically normal. So there we always get a normal subgroup of order P, and that completes the solution. So we seem to have said something about groups of order P square, that normal subgroups of order P always exist in any such group. Now we say something more. Now that we know such a subgroup exists, we will now say something about that subgroup, something extra. That is the next exercise. Prove that if a group G of order P, in a group G of order P square, any normal subgroup of order P must lie in the center of G. So the center of such a group must always contain any normal subgroup of order P. Let N be a normal subgroup of G of order P. Now because N is normal, we can consider the quotient group of G by N. And we are now going to say something about that group, since this quotient group is abelian, we have such an inclusion. there are many things to be said here, okay, about this statement. And this fact that the abelian, the quotient group being abelian implies this fact is coming from an exercise. We have already solved that exercise. You may recall we had such an exercise. See the part C of exercise 5 from the 7th section. But there is still one more thing to be said. How is G by N abelian? Look at the order of G by N. It's the order of G divided by the order of N. That means P. So G by N, because it is a group after all, it's a group whose order is a prime number. So by a previous exercise we can say that G by N is a cyclic group, and being cyclic it is abelian. So that's how it is abelian. And this is of course your commutator subgroup, which is also known as the derived subgroup of the group, which if you recall is this. You consider the set of all elements in the group which look like this. They are called commutators. Then you get a subset of the group. This subset will generate a subgroup. That subgroup is this thing. Okay, so now whenever you see such an inclusion, the immediate thing to do is to think of Lagrange's theorem. Because we are dealing with finite groups mostly, we can use Lagrange's theorem. Since the order of n is p, it follows from Lagrange's theorem that either G prime is the trivial group or G prime is equal to n, because the order of G prime by Lagrange's theorem should divide P. So it can either be 1, in which case we have that, and or it can be equal to P, in which case we have this. Now if this happens, then the group is abelian. If G prime is trivial, then G is abelian, and so n is contained in G, which now equals its center. So n is contained in the center. That's what we wanted, no? So we now assume that G prime is equal to N. Okay. Now again, just like the previous solution, we have to consider the center of the group separately by Lagrange's theorem. I think we haven't mentioned that Z is the center of G, but you can understand that in the context, in the present context, Z is always the center of G, unless stated otherwise, unless Z denotes something else. By Lagrange's theorem, either Z is trivial or Z equals the entire group G, or the order of Z is P. If Z equals, okay, let me just see one thing. Can we take care of both these things? Okay, no need, we won't shorten the proof in a significant way by doing what I was thinking of doing. If, let us go case by case. If the center equals G, then of course our normal subgroup is contained in the center, and we are done. If the order of the center equals P, then the quotient group this is abelian, just like we have here, what we have done here. We are now again doing with Z in place of N, and hence the center, which now plays the role of this N, contains the commutator subgroup, which now is equal to the group N. So in this case also, N is contained in the center. So there is only one more case left. We now suppose that the center is trivial. Okay. Now because the center is trivial and the group has p square elements, G is non-abelian, then G is non-abelian. Choose two elements A and B in G which do not commute. Non-abelianness allows us to choose two such elements, non-commuting elements. Such that AB and BA are different. Now what we will do, we will now consider the normalizer of A. The normalizer of A, let us recall, is the set of those elements in G that commute with A. Okay, and we have already seen that the normalizer of any element is a subgroup of the group. We know that this is a subgroup of G. We have, okay, so because it's a subgroup of G, again by Lagrange's theorem, either it's equal to the trivial group, or it equals the whole group, or it has order P. Now we are coming to that later, but first we see that two of these three possibilities actually do not occur. We have the normalizer of A not equal to the trivial group. Why? Because A itself belongs to the normalizer of A. A commutes with A, and A itself is not identity. Why? Because E commutes with every element, so E will commute with B, but A is not commuting with B, so A cannot be identity. So this cannot be equal to the trivial group, and the normalizer also cannot be equal to G, because B does not belong to the normalizer of A. For B to be in the normalizer of A, B should commute with A, which it does not. So that's why N of A is a proper subgroup of G. So by Lagrange's theorem, order of the normalizer must be equal to P. Okay. Okay, so the order of the normalizer is P, and this is again a situation in which we can apply lemma 291, because the order of the group, which is P squared, does not divide P factorial. So by lemma 291, the normalizer of A should contain a non-trivial normal subgroup of the original group G. If you think of that subgroup, if you call that subgroup N, then N is contained in the normalizer of A, and being non-trivial, N cannot have order 1. But because N of A has order P, so order of N by Lagrange's theorem must be equal to P, and that's why N of A should be equal to N, and hence N of A must be normal. We have gone through this argument once, so we are not repeating that. We will simply write hence by lemma 291, NA is normal in G. Okay, so NA is normal in G, and similarly, whatever we have done with A, we can also do with B. A is nothing special. B plays the same role as A is playing. Similarly, the normalizer of B is a normal subgroup of G of order P. So we have got two normal subgroups of G of order P. And they are different because this one contains A but this one does not contain A. We can mention that since A belongs to the normalizer of A, but A does not belong to the normalizer of B. Okay, now both of them have order P and they are different. So by Lagrange's theorem, we have this: their intersection should be trivial. Do you see how often Lagrange's theorem is used in the study of finite groups? It is arguably the central thing that is used again and again. There are other things also, but this is the most important one. Now, how are we getting this fact that the intersection is trivial? You see, the intersection is a subgroup of, say, NA. Okay, because it is a subgroup, we know that the intersection of any two subgroups is itself a subgroup, and it is contained in both of them. Actually, we just need to consider one. It is contained in N of A, so its order should divide the order of N of A, that is P. So it is either 1 or P. Suppose it is P. Okay, then I need ink, give me a moment. So if we suppose that possibility that its order is N, then this is a subset of N of A and both the sets have the same order, so they must be equal. But this equality tells us what? That N of A is contained in N of B. then that is the only case in which this intersection will be n of a. But again you use that fact that both these sets have the same number of elements, so that implies NA equal to NB, contradicting this thing. So this cannot have p elements, it must have only one element, that is the identity element. That's how we are getting this trivial intersection. And now recall another exercise that we have seen previously. We saw that if in a subgroup, if in a group G, we have two normal subgroups N and M, such that their intersection is trivial, then the elements of N commute with the elements of M. That is, if you take any element from N and any element from M, then Nm is equal to Mn, and we are going to refer to that exercise precisely. Now, can we apply this exercise? What is our N? Our N is N of A and M is N of B. We have shown that both of them are normal and their intersection now is trivial. But by exercise 12, of section 2.6, we then have CD equal to DC for all elements C in the normalizer of A and all elements D in the normalizer of B. In particular, AB is equal to BA, because A belongs to the normalizer of A and B belongs to the normalizer of B, and this directly contradicts the choice of A and B. This is a contradiction, and so our supposition is wrong from where this whole thing is stemming. That is the case where the center is trivial, it actually does not occur. And in the other cases, we have shown that our original subgroup N of order B is always contained in the center. So we are done, and this completes the solution. And then the next one again says something about groups of order p square. Using the result of this previous exercise, Exercise 6. Prove that any group of order p square is abelian. Okay, so the fact that now the situation is like this. No, this is our group. In the first exercise in this video, we proved that there is a subgroup H of order P, which is normal. Then in this previous exercise, we showed that any such normal subgroup of order P must be contained in the center of the group. So by Lagrange's theorem, the center either has order P or P square. It cannot be, of course, equal to the identity which now follows from this previous exercise. We will now have to show that it cannot be equal to P, that the center has order P square, so it's all of G, and that tells us that G is abelian. Okay, so and the beginning is like that. Let this be the center of G. By the previous two exercises, the center is either equal to G or the center has order P. If the center is equal to G, there is nothing to show. So suppose that the center has order P. By the way, when we considered the center in the previous exercise, or I think the one before that, at one point we considered this, no? We should remember that we can use that exercise to conclude that the subgroup by which you are forming this quotient contains the commutator subgroup. In order to be able to apply this exercise, you should keep in mind that the subgroup you are considering is normal, so that you can form the quotient group, and the center is always normal in any group, so there is no problem. And again we are now going to use this. Since the center is, it's well known that the center is normal, so we don't even bother to mention that. We straight away consider the quotient group, this. Since its order is P, so now we will not simply use abelianness of G by Z, we use the sharper fact that this quotient group is in fact cyclic. So cyclic means it will be generated by an element. Now elements in this are cosets of the center. So we choose one such coset to be the generator. Let this be generated by this coset, where this G is of course some element of the original group. Okay. Now we take any two elements in the original group. Let G1 and G2 be any two elements. In fact, let's just write that, mention that they are arbitrary elements. Be any elements. Then if we consider the cosets of the center by these elements, then these cosets will be some integral power of this generator Zg. Oh, this is G1, sorry, and like that. This is also some integral power of Zg. For some integers I and j. So this coset Zg1 equals that coset Zg to the power I. Now since G1 itself as an element, it belongs to this coset, so G1 should also belong to that coset. This implies G1 is equal to Z1 G to the power I, and just like that G2 is equal to Z2 G to the power J. For some central elements Z1 and Z2. Now from these forms of G1 and G2 we will be able to show that they commute. Let us show it in the middle. G1, G2 is Z1 G to the power I, Z2 G to the power J. There is no need to use any bracket because we have already proved the generalized associative law, which allows us to not write any brackets and still get a well-defined product. Now Z2 is a central element, so it will commute with G to the power I, and we will get this. Okay, so in the middle we have flipped these two elements, we have interchanged them. Now these two also commute because they are after all powers of G. If you want to be more specific, you can write intermediate steps like this. Here we have used one of the rules of exponents, which can be written as this, that equals this. Oh, and at the same time, without keeping those central elements, I mean in particular Z1 inactive, let's change that also, I mean its position. Because these are after all central elements, we can write 2 here, 1 here. Now again these two will commute, Z1 and G to the power J, because Z1 is central. So you now see Z1 G to the power I, we have it on this side, that is G1, and this thing is G2. So any two elements G1 and G2 in G commute. Thus G is abelian, but the solution is not over yet. The thing is that we have obtained this conclusion under the supposition that the order of the center is P. Okay. But then the order of the center, which is equal to the order of the group, is P square, which contradicts the supposition. Thus, the supposition is wrong and we must have this equal to P square. Hence, the center equals the whole group, that is G is abelian. Okay, so here we have seen a peculiar situation arising where if we forget where things are coming from, we may stop here itself, leaving the solution incomplete. So now it's complete, and we will solve another one. So that means every group of order P square is abelian. We will see this result proved for us again later on in the text much more simply using something known as class equation. But these exercises show that even without those advanced tools, one can systematically go forward using only whatever we know so far and still conclude this thing, although somewhat in a more lengthy manner. If P is a prime number, prove that any group G of order 2p, this time not p square but 2p, must have a subgroup of order P and that this subgroup is normal in G. So the conclusion is like groups of order p square, but here the order is 2p and p is any prime. So we look at the simplest case first and then go to the general one. We know that any group G of order 4 is abelian. So this is the case when P is 2, that is the smallest value P can take. And this is something we have already seen in one exercise previously. In fact, we proved that any group of order 3 or 4 or 5 is abelian. Non-abelian groups start from order 6. So this is abelian, and because 2 divides 4, so here we can again use Cauchy's theorem of for abelian groups and conclude that there is an element of order 2. A not equal to E in G such that A square is equal to E. These two things ultimately are together, they are equivalent to the statement that A has order 2. the cyclic subgroup generated by that element A has order 2, because the generator has order 2, and hence our and is of course normal, because after all this subgroup is a subgroup of an abelian group, so it is automatically normal. So whatever we are desiring here is true when b is equal to 2. We have got a subgroup of order 2 which is normal in the original group. So we now assume that our prime is greater than 2. It's an odd prime. 2 is the only even prime. This is now an odd prime. Okay. If we can find a subgroup H of G of order P, then the index of H in G is 2p divided by p, and hence H would be normal. We know this exercise. We have seen in one previous exercise that any subgroup in a group of order 2, index 2 is normal in that group. So normality, again, just like before in groups of order p square, here is also a consequence of the order being p. So it's enough to find a subgroup of order p. If our original group is abelian, the result follows from Silhous Theorem for abelian groups. What is Silhous Theorem? This is also something we have already proved in the section on homomorphisms towards the end of that section. Silhous Theorem says that if we have a finite abelian group G, whose for which there is a prime number p such that p to the power alpha, where alpha is a non-negative integer, divides the order of G, but the next higher power, p to the power alpha plus 1, does not divide the order of G, then G has a subgroup whose order is this highest power of P dividing the order of G. For us, the order of G is 2P. Okay, so the highest power, and note one thing, that now P is odd. So the highest power of P that divides this order is P itself. So that means by Silhous theorem, in our G, we would find a subgroup of order P. So we are done if the original group is abelian. So that means we have to now assume that it's non-abelian. We will now consider that case. Now assume that G is non-abelian. Okay, now by corollary 1, I think, yes, by corollary 1 to Lagrange's theorem, what that corollary says, it says that the order of the group is divisible by the order of any element in it. Okay, element orders divide the group order, and here the group order is 2P, so the element orders can either be 1 or 2 or P or 2P. However, no element order can actually be equal to 2P, because if you are able to find an element whose order is 2P, then the cyclic subgroup it will generate will also have order 2P, giving you everything in the group. That is, it would make G itself cyclic and hence abelian, which would contradict our case that it's now a non-abelian group. So no subgroup of no element of order 2P. Element of order 1 is always there in any group, which is the identity element. Besides these two possibilities, we have 2 and P. That means every non-identity element in our group now has order either 2 or P. That's what we are going to write, and that is coming from corollary 1 to Lagrange's theorem, along with non-abelianness of the group, of course. Each or every, whatever you want to write, every non-identity element in G has order 2 or P. Keep in mind, we are not even mentioning that elements cannot have order 2P. Those things are there in the background. Okay, it's not, everything need not always be shown. but all the non-identity elements of G cannot have order 2 since G is non-abelian, because in one previous exercise we have seen that if that happens, then you can in place of this statement that all non-identity elements have order 2, you can say something else also, that the square of every element equals the identity. This equation tells us that the order of A is either 1, which is only when A itself is identity, or it is 2 when A is not identity. If this happens in a group, then the group is automatically abelian. In such a group, every element is its own inverse. And the exercise where we proved this is this. See exercise 10. After the third section. So that means there is at least one non-identity element in G which has order P. So there exists an element A in G whose order is P. So naturally now you know what we would do. We would consider the cyclic subgroup generated by this element. It will also have order P. Then has order P, and we are done. In any case, we have produced a subgroup of order P, and which we have seen, because such a subgroup has index 2, it is automatically normal. So I am ending the video here. After this there are, I think, 2 more exercises where we explore groups whose orders look like this: PQ, where P and Q are distinct primes. We have seen what happens when they are equal, and we have also seen, in this type of orders, this case is also included, 2P, where say P is 2, or you can take Q to be 2. So we will see this in the next group theory video. And now, after this video, we have our exercises of abstract algebra by Lee. That video is also there. So see you in that video next.